Hey guys, so sorry about the delay in getting this to you. I didn't get a chance to do this before. Alright, so in this video I'm going to talk about a few things that I was not able to talk about on last Thursday. Alright, so in this video I'll just quickly talk about what the project 4 is, what you'll be doing, and then talk about the Hackett, Lilly, and Wilson's correction method, and also introduce Schlieren photography. So, we are slowly getting into this flow visualization area, and it is something that, it can be discussed in a video because, if I were to do this in class, I would ask you what are the different type of information that you can get out of flow visualization. We'll do that next Thursday, but for now, we'll just get started with student photography because I think it's pretty interesting. All right, so project 4, question 1. I'm pretty sure you guys all got the email about the handout. So the handout should be attached in the assignment tab in Isidore and also posted on the announcement page. So the first question is it'll ask you to use the tunnel correction methods that we discussed in class to quantify the effect of solid blockage, effect of weight blockage, and the effect of streamline curvature. One thing that I didn't put it in the project 4 is the effect of horizontal buoyancy. So if you can do that as well, that'll be great because it's just for you to see how much the boundary layer growth affects the measurements in the tunnel. All right. So you'll be employing these different blockage corrections for the lift coefficient, drag coefficient, pitching moment coefficient on a NACA 0012 wall-to-wall model placed in the aerolab test section. So our aerolab test section has 30-inch cross section, and you can assume you can take a chord of 2 inches, 4 inches, and 8 inches. So when you do that, just so that you can see what's the blockage ratio and how the blockage ratio affects the the measurements that you take. So one of the things that you should you can also do is look at the blockage corrections as a function of angle of attack. As you know, as you pitch the angle of attack, you change the angle of attack, your frontal area exposed to the flow increases. That increases the blockage ratio. That influences the flow as well. So this is the first problem that you'll be working on. Again, we'll talk more about in class on Thursday, but if you have any questions just about this, just let me know as well. So again, you look at the handout that I gave last time, all the equations are listed in there. I know there are a lot of equations for weight blockage, solid blockage. Just when you code it, you're not doing this by hand, so you can code it in MATLAB and see how different equations correspond to different variations in blockage, right? Just so that you get an idea of what the equation does. All right. So the question 2 asks you to look at a very interesting paper written by Dr. Altman back in 2011. He published a paper called, with his grad student Ian Ross, Wind Tunnel Blockage Corrections Review and Application of Savonius Vertical Axis Wind Turbines. So what this does is that, what this paper, what's described in this paper is the Savonius turbine, which is basically the vertical axis turbine. And they take the vertical axis turbine and they scaled it at different scaling ratios and looked at how the wind tunnel influenced the measurements that you get from the vertical axis turbine. So it's a very interesting study, just purely meant to understand the effect of wind tunnel on power measurements of the turbines. So they used one of the methods they used is what is called Hackett, Lilly, and Wilson's method to correct for the efficiency of the turbine. So we didn't quite cover this in class. Well, we peripherally talked about this type of method, but we didn't really put a name to it. So in this video, now I'm going to talk about what you can, what the correction method is and how you can use it to correct for the power measurements of the turbine, right? So this correction method was developed by Lockheed scientists Hackett, Lilly, and Wilson. Again, this was back in 1975 or 76. So this is primarily a solid and wake blockage correction that involves tunnel wall pressure measurements. All right. So imagine you have an object in the test section right? And of course, you have a solid blockage, and also you will have a wake blockage. This is just a qualitative wake I drew here. Usually, depending on the Reynolds number, the wake can be either larger or thinner based on what type of body you're looking at too. All right, so when you place it, you know that the flow is going to accelerate around the curvature, because not only just because of the curvature, but also you have this Venturi effect. So when you do that, obviously, as we talked about in class, that it changes the coefficient measurements that you're taking from the tunnel, right? So what Hackett, Lilly, and Wilson did is they approximated sources, strength, and a lot of the elementary flows we talked about in aerodynamics class. So I put a name and put these dots here, but think of this as a source and another source and a sink here. Okay, so basically what they did is they changed the variations of the strength of the source sink, so that they kind of get this shape, whatever the shape is. So then they can from there they describe how the pressure variations change across the body. All right. So let me describe some of the mathematics behind it so that now you get a better idea, right? So um, you know that it involves tunnel wall static pressure measurements. Okay, but what are we interested is their main main correction method focuses on the static pressure measurements across the surface, right? That's what they were hoping to get out of this correction method. And in order to understand that, they have to understand how the flow is accelerated through this area right there, right? So let's take a hypothetical wind tunnel. On the walls, when you have uniform flow without any model in it, the CP can be represented by this equation, where over here, this is the local velocity, right? So without any model, the local velocity will be the free stream velocity by itself, right? So now you guys know what the CP equation is. So when free stream matches the local velocity, then the CP will be 0, right? Now imagine you have this, an object in here. You know that the flow is going to constrict here and the velocity is going to increase, right? Now, and because of that, the CP will also change, right? So Hackett, Lilly, and Wilson came up with this equation right here to account for the velocity increase and get the corrected pressure coefficient variation across, I'll draw an axis here, X and Y. Again, I'm drawing this with my left hand, so it's even with my right hand, it looks like that on PowerPoint, but anyway. Right, so this is the corrected version of the CP, the coefficient of pressure, right? So if you look at the formula, it has the uncorrected coefficient of pressure, -1 divided by 1 plus delta U, which is the velocity that gets accelerated, or the increase in velocity due to the tunnel wall, divided by U infinity square, right? So if you think about it, this correction only works if you know what the acceleration or what the incremental in velocity is, right? Let's think about it, right? How can we actually get that variation? How can we understand the increment in velocity? So that's why we actually look at tunnel wall measurement, right? When you have the model, there will be a change in coefficient of pressure across the tunnel walls due to the object being there. And that is indicative of what the increment in velocity is, right? So you know that we can rearrange the CP equation right here in terms of, it's basically the same equation, but you have this increment in velocity, right, and the local surface on the wall. So when you do that, and you know that there will be a change in CP, right? So when you expand this out, you can write, U infinity gets canceled, and then you'll get this ratio, right? From there, you can rearrange the equation and get to this equation right here. If you look at it, this is the increment in velocity, right, that you get because of the object being there. And this CP is the difference between the CP without the model and CP with the model, right? So that means if you install static ports across the surface, the tunnel wall, you can understand, well, you can actually get the pressure variations, subtract that from the mean or the CP without the model, then you will get this delta CP, and from there you can find what delta U is. If you have an airfoil or any bluff body, you can use this equation to put it in here, and then you can get the CP variation across the object. Once you know CP, you know that you can also calculate lift and drag measurements, right? So this is basically what they came up with. So in the homework, what you can do is, I kind of put a model in here. So in Alpin's and Ian's papers, they put this the vertical axis turbine in the tunnel, and they actually took tunnel wall measurements based on the scale of the rotor. So, and it's you can see that in figure 14 in their paper. So what you'll be doing is just pick any of the cases here. The different lines represent the different RPM and tip speed ratio of the turbine, right? So the free stream was set at constant, which means here you get 50 miles an hour coming over it, but you know that because of the blockage, the wall will see some pressure variations, and it's right. And look at that. It's not uniform at all. There is a pressure variation across the turbine. So a little about how the x-axis is aligned, and I think it's aligned with the center. So this is basically 0, and then here you have negative and positive. But you can read the paper and look at how it's oriented. But this is what I remember from my memory. And also, it'll be interesting to see what the blockage or the effect is at higher speed, or at the higher CP variation. It's interesting to actually see that the higher variation in CP occurs at a lower tip speed ratio and at a lower RPM of the turbine, right? So again, it's pretty interesting. All right, so this is what you have to do for question 2. Again, if you have any question, just let me know. All right, so next is the Schlittern imaging.